There are things about the universe you're never told, not because they're secret, not because there's a conspiracy, but because they're so strange, so counterintuitive, so fundamentally unsettling that they don't make it into popular science books or documentaries or even most physics classes. I've spent my entire career working on the deepest questions in physics, and I've discovered things that most people never hear about, things that would change how you see reality if you knew them, things that even many physicists prefer not to think about too carefully because they're so disturbing to our intuitions. Let me tell you what you're never told about the universe. The uncomfortable truths that physics has discovered but that rarely get discussed outside of specialized research seminars. First thing you're never told, the universe might be finite in a way that makes no sense. We talk about the observable universe being finite, bounded by our cosmological horizon. That's fine. That makes sense. But the universe itself might be finite in total information content. The holographic principle says the maximum information in any region is proportional to the area of its boundary, not its volume. If our universe has a cosmological horizon, then the total information content is finite, proportional to the horizon area. This means there are only finitely many possible quantum states our universe can be in, only finitely many possible histories, finitely many possible configurations. The number is huge, unimaginably huge, but finite. What does this mean? It means in some sense the universe is like a finite computer running a finite program. There are only finitely many things that can happen, only finitely many bits of information total. This is never discussed in popular accounts because it's deeply weird. We like to think of the universe as infinite in possibilities, unbounded in potential, but fundamental physics suggests it's finite, bounded, limited. You're never told that the universe has a maximum information capacity and that maximum is finite. Second thing you're never told, most of the universe is completely inaccessible to us and always will be. Not just practically inaccessible, but fundamentally in principle forever inaccessible. The cosmological horizon is not just the current edge of what we can see. It's a fundamental boundary. Regions beyond it are causally disconnected from us. Light from there will never reach us. We can never go there, never communicate with there, never get any information from there. And because of dark energy and accelerating expansion, this horizon is not expanding. It's roughly fixed, maybe even shrinking. More and more galaxies are crossing our horizon and disappearing from our observable universe forever. In 1 trillion years, most galaxies we see now will have crossed the horizon. Future astronomers will see an empty universe, just our local group of galaxies and nothing else. All evidence of the Big Bang, of cosmic expansion, of the vast universe will be gone. You're never told that we're in a special epoch, maybe the only epoch where we can see the larger universe, and that this is temporary. Future civilizations will be cosmologically blind. Third thing you're never told, quantum mechanics says nothing is real until you measure it, and measurement is not well defined. Before measurement, particles don't have positions, don't have velocities, exist in superpositions of being in multiple places at once. But what counts as a measurement? Does it require consciousness? Can a machine measure? Can an atom measure? Where exactly does the quantum world end and the classical world begin? Nobody knows. This is the measurement problem, and it's been unsolved for nearly a century. Every interpretation of quantum mechanics gives a different answer, and we have no way to test which is right. Some say consciousness causes collapse. Some say there's no collapse, just branching into many worlds. Some say there's an objective collapse mechanism we haven't discovered. Some say the question is meaningless. The truth is, we don't understand measurement. We don't understand how the quantum world gives rise to the classical world we observe. We don't understand the role of the observer. And this is not a minor technical issue. It's a fundamental gap in our understanding of reality. You're never told that physics doesn't understand how the world becomes definite, how possibilities become actualities, how measurement works. Fourth thing you're never told, the laws of physics might be different elsewhere. We assume the laws we discover are universal, applying everywhere and every when, but that's an assumption, not a fact. In eternal inflation and the multiverse, different bubble universes can have different effective laws, different constants of nature, different particles, and forces. What we call the laws of physics might just be the local laws in our bubble. And even in our universe, the effective laws change with energy scale. At low energies, we have the standard model. At higher energies, new physics appears. At the Planck scale, space-time itself breaks down, and the laws must be completely different. The laws of physics are scale-dependent, regime-dependent, possibly location-dependent. There might be no universal laws, just effective laws valid in particular contexts. You're never told that the laws of physics might not be universal or fundamental, just local and emergent. Fifth thing you're never told, time might not be fundamental and might not even exist at the deepest level. The Wheeler-DeWitt equation for quantum cosmology has no time in it. Time emerges when you divide the universe into subsystems and use one as a clock. Different choices of clock give different times. Time is not unique, not absolute, not fundamental. It's an emergent bookkeeping device. And the arrow of time, the direction from past to future, is thermodynamic, not fundamental. It comes from increasing entropy, from coarse graining, from our limited knowledge. At the microscopic level, dynamics are time symmetric. The flow of time, the sense of past and future, the feeling that time passes, all of this might be illusions, artifacts of how we, as thermodynamic systems, experience the universe. You're never told that time might not be real, that it's emergent and observer-dependent and possibly illusory. Sixth thing you're never told, empty space is not empty. The vacuum is full of quantum fluctuations, virtual particles popping in and out of existence, fields fluctuating at every point. And these fluctuations are real. They affect atomic energy levels, they create the Casimir force between plates, they make black holes radiate. The vacuum has structure, has energy, has physical effects. But here's what's really never told. The vacuum energy, the energy density of empty space, is wrong by a factor of 10, 120. That's not 120 orders of magnitude. That's 10 to the power 120 orders of magnitude wrong. When we calculate what the vacuum energy should be from quantum field theory, we get a number that's incomprehensibly larger than what we observe. This is the cosmological constant problem, and it's the worst prediction in the history of physics. Why is the vacuum energy so small? Why is it not zero? Why is it the particular small value we observe? Nobody knows. It's a complete mystery. You're never told that our best theory makes the worst prediction ever, off by more than 100 orders of magnitude, and we have no idea why. Seventh thing you're never told. Most of the universe is made of stuff we don't understand. Dark matter is about 27% of the universe's energy content. We know it exists from gravitational effects, but we don't know what it is. It's not made of any known particles. Dark energy is about 68% of the universe. We know it's causing accelerating expansion, but we don't know what it is. It might be the cosmological constant, it might be a field, it might be something else entirely. So about 95% of the universe is made of things we don't understand. We only understand the ordinary matter, the 5%, the stuff made of atoms. Everything else is dark, unknown, mysterious. You're never told that physics only understands 5% of what the universe is made of. The other 95% is a mystery. Eighth thing you're never told, the universe might have no beginning. The Big Bang is often described as the beginning of the universe, the moment when space and time came into existence. But that's not quite right. The Big Bang is the beginning of the hot, dense phase of expansion. It's where we can't extrapolate backward anymore with our current theories. But it might not be the absolute beginning. In some models, like eternal inflation, there's no beginning. The universe has always existed, always been inflating somewhere. Our Big Bang was just a local event in an eternally existing multiverse. In some quantum cosmology models, the universe doesn't have a beginning in time, because time itself is emergent and doesn't exist at the fundamental level. Asking what happened before the Big Bang is like asking what's north of the North Pole. The question assumes a framework that doesn't apply. You're never told that the Big Bang might not be the beginning, that the universe might be eternal or might not have a temporal origin in any meaningful sense. Ninth thing, you're never told, black holes might not have interiors. The classical picture is that black holes have an event horizon and an interior region where everything gets pulled to a singularity. But quantum mechanics and the holographic principle suggest a different picture. All the information about a black hole is encoded on its two-dimensional event horizon. The interior might be a holographic projection, an emergent description, not a real independent region of space. When something falls toward a black hole, from the outside it never crosses the horizon. It freezes there, its information spreading across the surface. The interior description, where things fall through and hit a singularity, might be a complementary description, valid from a different perspective, but not describing an independently existing region. Black holes might be fundamentally two-dimensional objects, horizons without interiors, and all our three-dimensional thinking about them might be emergent approximation. You're never told that black hole interiors might not exist, that they're holographic illusions rather than real regions of space. 10th thing you're never told, the universe is probably not computable. A computable universe would be one where you could, in principle, simulate it on a computer, calculate its future evolution from initial conditions. But quantum mechanics involves true randomness, not just apparent randomness from hidden variables. Bell's theorem and experimental tests show this. The randomness is fundamental, not deterministic chaos. And self-reference creates uncomputability. Gödel's theorems show that sufficiently complex formal systems can't completely describe themselves. The universe contains observers trying to understand the universe, creating a self-referential loop. A universe containing observers sophisticated enough to ask questions about the universe probably can't be fully computable. There are questions about the universe that can't be answered by any algorithm, including questions the universe itself instantiates. You're never told that the universe might be fundamentally uncomputable, containing truths that can't be calculated by any procedure. 11th thing you're never told, consciousness might be necessary for quantum mechanics to work, or consciousness might be completely irrelevant, and we have no way to tell which. Some interpretations, like von Neumann-Wigner, say consciousness causes wave function collapse. The quantum state remains in superposition until a conscious observer makes a measurement, then it collapses. Other interpretations, like many worlds or objective collapse theories, say consciousness plays no special role. It's just another physical process. Quantum mechanics works the same whether anyone's watching or not. Experiments can't distinguish these. Consciousness is correlated with measurement outcomes, but we can't tell if it's causing them or just experiencing them. We can't get outside our own consciousness to test. The role of consciousness in physics is either fundamental or irrelevant, and we don't know which, can't test which, might never know. You're never told that the relationship between mind and matter, between consciousness and quantum mechanics is completely unsettled and possibly untestable. 12th thing you're never told, space-time might be discrete at the smallest scales, made of indivisible chunks, quantum geometry. Loop quantum gravity predicts this. String theory suggests it. The Planck length might be the smallest meaningful distance. But we can't test this. The Planck length is 10, -35 meters, far smaller than anything we can probe with any conceivable experiment. We're limited by the uncertainty principle. To probe such small distances requires such high energies that you'd create black holes. There's a fundamental limit to how closely we can examine space-time. We might never know if it's discrete or continuous at the smallest scales. The question might be empirically unanswerable. You're never told that there are fundamental limits to observation, questions we can never answer experimentally, mysteries that might be permanent. 13th thing you're never told, the fine structure constant, the number that determines the strength of electromagnetic interactions, is approximately 1/137. We measure it, we use it, but we don't know why it has this value. Richard Feynman called this one of the greatest damn mysteries of physics. Why 1/137 and not some other number? Is it fundamental or derived from something deeper? Is it the same everywhere in the universe? We've measured it to incredible precision. We know it varies slightly with energy scale, but we have no theory that predicts its value. It's a free parameter put in by hand, and we don't understand it. And there are about 20 such parameters in the standard model. Masses of particles, coupling constants, mixing angles, all measured but not predicted. Our best theory requires 20 numbers we can't derive from anything more fundamental. You're never told that physics doesn't explain about 20 fundamental numbers that determine how the universe works. We measure them, but we don't understand them. 14th thing you're never told. The information paradox for black holes was supposed to be solved, but there's still no consensus on the solution. I spent decades arguing with Stephen Hawking about this. When a black hole evaporates through Hawking radiation, does the information about what fell in come back out, or is it destroyed? Quantum mechanics says it must come back out, but Hawking's calculations suggested it's destroyed. Most physicists now believe information is conserved, that it comes out in subtle correlations in the radiation. But exactly how this happens, what the mechanism is still debated. Some say it's in the Hawking radiation all along. Some say it comes out in a final burst. Some say the interior and exterior are the same degrees of freedom described differently. Some say the horizon has a firewall. The details are not settled. You're never told that one of the biggest paradoxes in theoretical physics is sort of solved, but the solution is still controversial and incomplete. 15th thing you're never told, the universe might be a simulation, not in the sense of definitely being one, but in the sense that we can't rule it out and have no way to test it. If we're in a simulation sophisticated enough to fool us, how would we know? The simulators could make physics appear consistent, make experiments, give expected results, hide all evidence of the simulation. Some argue that if advanced civilizations create many simulations, and simulations can contain conscious beings, then statistically we're more likely to be in a simulation than in base reality. Others argue this is unfalsifiable metaphysics, not science. But the point is, we can't rule it out. The universe could be a computation running on some vast computer in a larger reality, and we'd have no way to tell. You're never told that the simulation hypothesis is unfalsifiable, that we might be living in a simulation and can never know for sure. 16th thing, you're never told. Infinity might not exist in physical reality. We use infinity all the time in physics, infinite space, infinite time, infinitesimal points, limits going to infinity. But these are mathematical idealizations. In reality, space might be finite or bounded, Time might be finite or emergent. The continuum might be an approximation of something discrete. Infinities in calculations might be signs. We're using the wrong framework. Every time we get infinities in our theories, black hole singularities, the Big Bang singularity, ultraviolet divergences in quantum field theory, it's a sign the theory is breaking down, that we need a better theory. Real physics might be fundamentally finite. Infinity might be a mathematical convenience, not a feature of reality, but we use it constantly, often without acknowledging this assumption. You're never told that infinity might not be real, that it's a mathematical tool we use, but shouldn't reify into physical reality. 17th thing you're never told. The wave function of the universe might include all possible universes in superposition. In the many worlds interpretation, every quantum measurement creates branching, and all outcomes happen in different branches. Extend this to the whole universe, and you get a universal wave function that contains all possible histories, all possible configurations, all possible versions of reality. You're in one branch, experiencing one history. But the wave function contains all branches, all versions of you experiencing different histories. They're all equally real, all part of the quantum state. This is not speculative fantasy. It's a straightforward consequence of taking quantum mechanics seriously and applying it to cosmology. It's what the Schrödinger equation predicts if there's no collapse. You're never told that quantum mechanics might imply everything that can happen does happen in some branch of the wave function. 18th thing you're never told. Observers might be necessary for the universe to exist. Not in a mystical sense, but in a subtle quantum mechanical sense. In the delayed choice, quantum eraser experiment, measurements you make now can affect the apparent behavior of photons in the past. The past is not fixed until you make a measurement that retroactively determines it. John Wheeler proposed the participatory universe. Observers, through their measurements, participate in creating the reality they observe. The universe is not a pre-existing thing we passively discover. It's something we actively participate in defining through our observations. This is controversial, not mainstream, but it's a logical consequence of taking quantum mechanics seriously. Observation might not just reveal reality, but help constitute it. You're never told that observers might play a fundamental role in creating reality through observation, that the universe might require observers to exist in definite form. 19th thing you're never told. The Anthropic principle might be the explanation for many features of the universe, and if so, we can never do better. Why is the cosmological constant so small? Why are the constants of nature fine-tuned for life? Maybe because we exist. In a multiverse with different constants in different regions, we necessarily find ourselves in a region compatible with our existence. Selection bias explains the apparent fine-tuning. If this is correct, many questions we thought were deep physics questions turn out to be anthropic tautologies. We can never predict the constants, never explain them from deeper principles, because they're essentially random, and we're selected to observe values compatible with observers. This is unsatisfying to many physicists who want fundamental explanations, but it might be the truth. We might live in a universe where some features are explained only by if they were different, we wouldn't be here to ask. You're never told that anthropic reasoning might be the final answer to many deep questions, and if so, those questions have no deeper explanation. 20th thing you're never told. We might be fundamentally limited in what we can know about the universe, not just practically, but in principle. Gödel's theorems, the halting problem, quantum indeterminacy, cosmological horizons, all point to fundamental limits. There are mathematical truths that can't be proven. There are computational questions that can't be answered. There are quantum properties that can't be simultaneously known. There are regions we can never observe. Reality might contain truths we can never discover, patterns we can never see, aspects we can never access. The universe might be fundamentally mysterious in some respects, not just unknown but unknowable. This is hard to accept. We want to believe that everything can be understood given enough time and effort, but physics is revealing limits to knowledge, boundaries we can't cross. You're never told that some truths about the universe might be permanently beyond our reach, that mystery might be fundamental and ineliminable. Now let me tell you why these things are never told. It's not conspiracy or censorship, it's that they're uncomfortable, unsettling, philosophically troubling. They challenge our basic assumptions about reality, knowledge, and existence. Popular science wants to tell inspiring stories about cosmic discovery, about understanding the universe. These truths are depressing, limiting, paradoxical. They don't fit the narrative. Even in physics education, we teach the parts that work, the solved problems, the successful theories. We don't dwell on the unsolved paradoxes, the foundational mysteries, the disturbing implications. And many physicists themselves don't like thinking about these issues. They focus on calculations, predictions, applications, the philosophical questions, the interpretational issues, the deep conceptual problems. These are often dismissed as not real physics. But they are real. They're what physics has discovered about the universe, and they're profound. They change how we should think about reality, about knowledge, about ourselves. You're never told these things because they're uncomfortable truths that don't fit our preferred narratives about science and understanding. Let me emphasize, these aren't fringe ideas or wild speculation. These are implications of our best theories, quantum mechanics, general relativity, thermodynamics, information theory. They're what the physics tells us when we take it seriously and follow the logic. Most come from unresolved problems at the foundations of physics. The measurement problem, quantum gravity, the cosmological constant problem, the information paradox, dark matter and dark energy, the interpretation of quantum mechanics. These aren't minor technical issues. They're fundamental gaps in our understanding, and they lead to these strange, never discussed implications about the nature of reality. You're never told that physics, despite its incredible success, still has huge gaps, fundamental mysteries, unresolved paradoxes at its core. Now, I don't want this to sound hopeless or depressing. These mysteries are what make physics exciting. They're the frontier. They're what drives research. Every generation of physicists works on these problems, makes progress, pushes understanding forward. But progress often means discovering that reality is stranger than we thought. Quantum mechanics was progress, and it made reality weirder. Relativity was progress, and it made space and time stranger. Holography is progress, and it's making dimensionality questionable. Understanding deepens mystery as much as it resolves it. We learn more about how strange reality is, how counterintuitive, how unlike our everyday experience. You're never told that scientific progress often makes the universe seem stranger, not more familiar, that deeper understanding reveals deeper mystery. Let me end with what I think is the most important thing you're never told. Reality at the fundamental level is nothing like your everyday experience suggests. Space, time, objects, causality, all of these are emergent approximations, valid at human scales, but not fundamental. The fundamental level is quantum, non-spatial, possibly non-temporal, holographic, informational, mathematical. It's described by equations, not pictures. It can't be visualized, only calculated. And this is permanent. We're not going to discover a deeper level that makes intuitive sense. The direction of physics is toward increasing abstraction, increasing mathematization, decreasing connection to everyday intuition. You're never told that fundamental reality is nothing like what you experience, and this disconnect is permanent and ineliminable. But here's the beautiful thing. We can understand it anyway. Through mathematics, through careful reasoning, through experimental testing, we can map this strange fundamental reality. We can make predictions, test them, verify them. The universe is stranger than we imagined, stranger than we can imagine. But it's comprehensible, not visualizable, not intuitive, but comprehensible through science. That's what you're never told about the universe. It's fundamentally mysterious, probably always will be in some respects, stranger than fiction, weirder than any religious or philosophical system ever proposed. And yet, through physics, we're understanding it anyway, bit by bit, mystery by mystery, even if the understanding reveals still deeper mysteries. The universe is not what you think. And that's the most profound truth you're never told